You know, there are some structures in the world that you see once and you never forget. And the Golden Gate Bridge, it's definitely one of them. It's this total icon, right? A symbol of amazing design and, frankly, some serious American ingenuity. But what I love about its story is that it's not just about steel and concrete. No, it's a story about doing something everyone said was impossible.
I mean, just look at that. It's a view you know instantly, right? Those two towers just cutting through that classic San Francisco fog. It's beautiful. But here's the crazy part. For decades, building a bridge there was considered a joke, a total fantasy. All the experts were saying, no way. The span is too long, the winds are insane, the currents are deadly. They called it the bridge that couldn't be built. So, how in the world did they do it?
All right, so let's get into it. An impossible idea. You might think the story of this bridge starts with some grand vision from an engineer, right? But actually, it starts with a total catastrophe. We have to go back to April 18, 1906. A monster earthquake hit San Francisco. And if that wasn't bad enough, fires just tore through the city for 3 days straight. Nearly 500 city blocks gone. Just ruins. But San Francisco is resilient, and out of all that destruction came this incredible rebuilding effort. The city started booming, growing like crazy, especially under a mayor named James Rolfe. And all that new growth, well, it led to a whole new kind of problem.
So, think about it. If you've ever seen a map of the area, you know San Francisco is basically on the tip of a peninsula. It's growing like wildfire, but it's trapped. It's got water on 3 sides. The only way to get to the counties to the north was by ferry. And that meant, you guessed it, epic traffic jams every single day. The city was literally choking on its own growth. A bridge wasn't just a nice-to-have anymore, it was absolutely essential.
So the city needs a hero, right? An engineer who can solve this impossible problem. Enter Joseph B. Strauss. This guy was no rookie. He'd built almost 400 bridges. So he steps up to the plate with his grand design. And his first idea, well, let's just say it didn't go over too well. So in 1921, Strauss shows everyone his plan, and crickets. No, worse than crickets. People hated it. It was this clunky Frankenstein's monster of a bridge, a cantilever suspension hybrid. The critics were savage. One of them called it an upside-down rat trap. Can you imagine? It was just ugly. And bam, the whole project, the one everyone was waiting for, just grinds to a halt.
But you gotta give it to Strauss. He didn't quit. After years of going nowhere, he and his team went back to square one. And what they came up with this time? Well, it was a total game changer. A pure suspension bridge. That graceful, elegant design that we all recognize today with those soaring towers and those beautiful, swooping cables. In 1928, Strauss was officially made the chief engineer. And this time, with this new design, the project was finally ready to go.
Okay, so this new design is beautiful, but how does it actually work? To really get why this thing is a masterpiece, we gotta talk a little bit about the science, the basic forces that let this giant chunk of steel and concrete just float in the air. It really boils down to a tag team of 2 forces, tension and compression. Think of tension as a pulling force, like a tug-of-war. Those huge main cables are constantly being pulled on, stretched by the weight of the road below. Then you've got compression, which is a pushing or squeezing force. All that weight from the cables gets transferred to the towers. The towers are being squeezed, pushing all that massive force straight down into these enormous concrete foundations deep in the earth.
And it's not just one kind of weight they had to worry about. They had to deal with 2 different kinds of loads. First, you have the dead load. That's the easy one. It's just the weight of the bridge itself. All the steel, the concrete, the cables, it's not going anywhere. But then there's the live load. That's everything that's moving on the bridge. All the cars, the trucks, the people. It's constantly changing. And the design had to handle both of these, all the time, without breaking a sweat.
So, okay, we've got the science down. But knowing the science is one thing. Turning it into an actual buildable blueprint for the longest suspension bridge on the planet? Yeah, that takes a whole other level of brain power.
And this part, to me, is just completely wild. Every single calculation for this bridge was done by hand. Let that sink in. No computers, no calculators, nothing. The guy behind all this heavy lifting was a design engineer and mathematician named Charles Ellis. For almost 2 years, he sat there with a slide rule, a pencil, and a stack of paper, and crunched thousands upon thousands of equations to make sure this thing would actually stand up.
And just to give you an idea of the scale we're talking about, look at this number. Those 2 gigantic main cables that hold up the entire roadway, They aren't just single, thick pieces of steel, no way. Each one is a massive bundle of 27,572 separate steel wires, all twisted together right there on site. I mean, the logistics of that alone are just mind-boggling.
But even with all the math done, there is still this massive, looming question. Could a bridge this big actually survive? I mean, this is San Francisco we're talking about. It's earthquake central. Plus, the Golden Gate Strait is basically a wind tunnel. So could this long, almost delicate-looking structure really stand up to Mother Nature at her worst?
And the answer lies in this genius quote from Charles Ellis. He used this perfect analogy to explain the design. He said if an earthquake hit, he'd want to be in a hammock strung between two giant redwood trees. And you think, why a hammock? Well, because it's flexible. It moves with the force. It sways instead of breaking. And that was the secret weapon of the Golden Gate Bridge. It wasn't built to be rigid. It was built to be flexible. It can literally sway almost 28 feet side to side. It dances with the wind and the earthquakes instead of fighting them.
So, the math checks out, the design is brilliant, revolutionary even. But paper is one thing. Now came the really hard part, the dangerous part, building it. This wasn't just about engineering anymore. This was about courage, a total leap of faith.
And you could feel the excitement in the air. On February 26, 1933, more than 100,000 people showed up at Crissy Field just to watch the groundbreaking ceremony. The wait was over. It was actually happening.
So where do you even start on a project this huge? You start with the anchorages, these absolute behemoths on either side of the strait. Think of it like building in layers. First, they build a giant wooden mold and pour a base of concrete. Then they add a special anchor block with all these steel girders and giant eye-bars. Those are what will eventually grip the main cables. Then they bury that whole thing in more concrete. And finally, a colossal block of concrete goes right on top. These things weren't just foundations. They were basically underground fortresses, designed to fight that incredible pulling force from the cables. And just like that, the work had begun. The blueprints were one thing. The calculations were sound. But now it was up to real men to turn it all into reality. They had to dive into those freezing, churning waters and climb to heights that would make you dizzy just thinking about it. Turning the blueprint into a landmark was going to take a kind of courage that you just can't calculate. The human story was just beginning.